Welcome everyone. My name's Mark Studley, and I'm going to be giving a talk to you called "Oh, the Compilers You'll Build," which is a little bit of a play on a Dr. Seuss book that I used to read to my daughter, which talks about all the amazing things that you're going to do when you grow up, and to not have sort of assumptions about what things you'll do, just have an open mind and try new things. And so I thought it'd be a good title for a talk about compilers. I work on a couple of open source projects called Eclipse Schoolmarm and Eclipse OpenJ9. These are open source projects that came originally from IBM, from their J9 Java virtual machine. So it's a bunch of technologies that we've open sourced for people to use to build all kinds of language runtimes, including JIT compilers and dynamic compilers. I've been a production JIT compiler developer since about 2002. So I've been working on mostly Java JITs, but more recently other kinds of JITs for about almost 17 years now. It seems like a long time. And I'm also creator of a library called the JIT Builder library, which is going to feature prominently in this talk. Unfortunately, I work for IBM. They like me to put all of these things up at the beginning of my slide just to really get you interested in my subject matter, so that you'll know that I don't want you shouldn't really listen to anything that I say.
Just a quick question. Does the legal department actually mandate this?
Yes, they tell us that we're supposed to put these things in our talks, because they don't want you to take anything I say without as many salt shakers of salt as you can think of. All right. So the basic outline of my talk here is I'm going to start off with kind of a bunch of musings from the pathetic mind of a production compiler developer. So these are things that I've been thinking about on weekends when I'm cutting the lawn. I've got an hour of menial tasks in front of me. And so I've been thinking a lot about how we use compilers to build software. And because I'm mostly a JIT compiler, back-end compiler developer, I'm mostly concerned with how we use compilers to provide high performance, to extract all of the features of the hardware that you possibly can into our software. And so that's a lot of the focus of the talk here. I'm going to have a second section of the talk which is more or less showing how the Eclipse Schoolmarm project is doing a bunch of things with the goal of trying to make compilers more accessible so that we can use compilers in more scenarios that are connected to how people develop software, and not just the traditional ways that we use compilers to compile languages. I have not one but two demos. So in those almost 2 decades of production JIT compiler and my research team before, or the time that I did research before that, in deep compiler development, I've almost never had the ability to give a demo. This year I've got 2 of them, so I'm on a good trend here. And the final part of the talk, I'll just give a few thoughts on where we might go from here. But actually I'm hoping that a lot of that could be driven by your thinking and not just from my thinking. So, started out from first principles. I thought back to when I was 16 years old and writing my first compiler, a wee lad. And I didn't actually check to see that this is what's written in the Dragon Book, but but this was my sort of original, foundational thought about what compilers were, right? You're translating software programs from one language into another, usually from a higher level language to a lower level language. But 60 years ago, when IBM released the first commercial Fortran compiler in 1957, John Backus's team was basically writing a program that translated software programs written in a language called Fortran. Who's written a program in Fortran here? Ooh, not very many. That's not surprising today. Nonetheless, that compiler was translating Fortran down to machine instructions. Fast forward 61 years, we're still basically using compilers to translate software programs written in a language, now it's more like Java or JavaScript or a host of other languages, to another language which is still usually machine instructions. Now, yes, there are lots of examples of compilers that are going from source to source and that are doing all kinds of very interesting things, but I think in general, across the entire software development industry, if you look at what people use compilers for, it's compiling a high-level language to machine language, and they're mostly not even involved in that, right? It's kind of a very quick step you do before you deploy your code. Maybe it even happens automatically as part of your CD pipeline. You may not even be aware that there's a compiler being used. Now, obviously, in those 60 years, we've done a lot, right? It's not that we've been standing still for 60 years, even though this model is kind of the same. You know, we now have compilers that run alongside the program at the same time that the program is running. We're collecting tons of profile data and using it to provide very aggressive optimizations and speculating even further about how we can improve the performance of that code. We're responding to the program, changing itself and its objects at runtime. So we're doing lots and lots of cool stuff. We haven't been standing still. Compilers are really a lot more sophisticated, but our generic model for how to employ compiler technology really hasn't changed in 60 years. So that role is, you know, translating operations and data structures, mostly written directly by programmers. Again, there are exceptions, but as a general rule, I think this is how compilers mostly get used, to generate efficient native code. And the source input to the compiler is, generally speaking, it's a program that's designed to solve a general class of problems, right? You're compiling something that's going to do a whole bunch of different possible things. And then we're relying on the compiler to kind of figure out how to optimize for a particular problem. But what if, instead of translating a program written by a programmer, we're actually trying to translate the data structures and operations of a precise problem being solved and conveying that directly to the compiler so that the compiler can generate efficient native code directly for solving a particular problem, as described by a program designed to solve a general class of problems. And I know what you're thinking. Lots of people have trouble writing a program to do something, let alone writing a program to generate a program that does something. And I think there are probably a lot of reasons why, as I wrote it on the previous slide, that wouldn't really work, right? First of all, the runtime cost to go and generate all the code that you would need to solve a particular problem is probably prohibitive, and it probably wouldn't pay off in a lot of cases. It obviously requires that you always have a dynamic compiler running at the same time as your program, because as soon as you run your program, it has to generate another program, and then you have to compile that. There are a lot of scenarios where you don't have the ability to use a JIT compiler. For example, we probably don't want our phones doing excessive amounts of JIT compilation just to, you know, answer an email. This particular email. And it would also require a very different approach to writing software. I don't consider that a blocker, and I'm kind of going to ignore that one. But I think there's a kernel of a good idea here, and that is to accelerate specific tasks by generating part of their programs at runtime and then using a dynamic compiler to optimize. Right? So this is basically, it's very similar to what a JIT compiler does. If you look at the interpreter as the thing that's running in general, trying to solve a general class of problems, right? It's trying to run code for any kind of method that you can possibly write. And the JIT compiler comes along and it says, oh, this particular method is important, so I'm going to JIT compile that one. I'm going to generate direct native instructions for this method. I don't get there, well, okay, there are projects where you get there by specializing the interpreter in order to generate the native code for a particular method. But most of the most successful compilers out there are not actually doing it that way. They're looking at the methods, the bytecodes of the method and generating that directly to native code and kind of ignoring what the interpreter does. So just to draw some pictures to show that, you start with an application, you have, as part of that application, some performance critical task, word in tasks. You've written a task accelerator which knows how to understand the problems that this thing is solving and generate a particular solution for the problem that you're actually solving at runtime. And then you're going to generate a specialized task runner that's sitting in your native code cache, and then there's some kind of hookup that has to go back and forth between the application and this now specialized task so that it can perform its job. And hopefully the transitions across this boundary are sort of lower frequency things so that you can stay in the high performance side as much as possible and only periodically have to go back and forth to the application. And in that way you can provide a much higher acceleration for the task that you're trying to complete. Now obviously this is not really a very new idea, right? There are tons of examples of things already doing this. I'm going to call out 3 here. Apache Spark is one of these that uses a Catalyst compiler to generate problem-specific Java bytecodes that are then shipped to all the runtimes, all the JVMs that run that code, and they run that Java bytecode that is specific for the problem that's being solved. the ROSI pattern language compiles the patterns that it's trying to search for into the bytecodes of another type of runtime called LPEG, which then does the actual pattern matching on the strings that are being sent through it. Finally, there are lots of regex engines that are creating different representations of the string that you're searching for. You know, like a non-deterministic finite automaton, for instance, that's very specific to the pattern that you're looking for, and then execute on that data structure. And there's even an example, which I pointed out here, there's this T-regex project in the Graal ecosystem that converts that NFA directly to native code, so that you're running native code to actually do this regex computation. And there's probably hundreds of other examples, but I'm going to ask the question, are these solutions really as effective as they could be? And in my opinion, they're really only a partial solution so far. Few of these, with the exception of the last one, go all the way down to native code. Most of them are doing a kind of source-to-source. It's a higher level to lower level, but it's not all the way down to native code. And so, you know, Spark, for example, generates Java bytecodes, which then need to be interpreted by a Java JIT compiler in order to actually generate native code. ROSI is generating the LPEG bytecodes, which are then interpreted by the LPEG runtime, or they can be JIT compiled by the JIT, which I actually wrote for LPEG. And I don't know of any other regex compiler that actually goes direct to native. Usually they go through the NFA or automaton approach, and then they convert back to native code. So the actual native code compiler here still probably has little to no idea what's going on. What are the actual characteristics of the problem being solved? Because it's limited by the expressiveness of the language that it takes as its input, right? You can imagine that Java bytecodes aren't very easy to change, and they may not be able to naturally express all of the characteristics of a SQL query that you're trying to run. And you're really limited in the JIT compiler front, where you can't afford to do lots of analysis to try to prove lots of things and derive things from this maybe not properly expressed computation that's been handed to you. So how could we do better? Well, one option is that we could use strong native compilers, right? We have some of those. We have LLVM, we have GCC, are the most famous ones, to generate native code directly, right? Just generate IL for the compiler, and all the way from the top to the bottom, you go straight to native code, and you'll be off to the races. But I don't think, my opinion again, that this is going to be a workable solution for a lot of programmers. In my opinion, it's a little bit too late for this one to work, because those native compilers are generally written in C and C++, you know, maybe it could have worked in the 1980s when there were fewer popular languages, right? Software developers knew C and C++. Most software developers knew C and C++ in the 80s. And developers were more generally knowledgeable about how compilers work and how processors work. If you look at the curriculum of your average computer science or computer engineer in those times, they were being taught how compilers worked. They were being taught how processors worked, how memory worked. However, dynamic JIT compiler technology, remember we're trying to do this at runtime, dynamic compiler technology was really at an infancy in the 80s. So maybe it wouldn't quite have worked. The challenges today, of course, are that we have tons of active programming languages, and we have people who've never even used C or C++. So asking them to descend into C, a language they don't know, to specify the intermediate language of some compiler that they don't have any idea how it works, is not really a workable solution, in my opinion. On top of that, many developers have little idea how processors actually work, or they've never taken a basic compilers course, you know, let alone the details of how sophisticated dynamic just-in-time compilers are operating. I'm not trying to insult anyone here. I think it's just a reflection of how our industry has moved up the chain, and we're looking at higher level tasks, and people are very successful without knowing this knowledge, so why would they invest to learn it necessarily? So if we want to solve a problem like this in this decade now, I think, you know, 4 characteristics that I'm going to call out as things that we have to do here are, it has to be easy to use for non-compiler developers. We can't be expecting people to have lots of compiler development knowledge in their heads. It has to be available natively from lots of different languages, because you can't always count on people being able to come down to the lowest common denominator where the compiler technology currently generally lives. We need a dynamic compilation story that can make it cost effective, because You know, if I can't get the code fast enough to make a difference in the execution time of the task that I'm trying to accelerate, that doesn't make any difference. And finally, obviously, it does still have to be backed by a strong cross-platform dynamic native compiler technology. And so at this point, I'm going to transition into how the Eclipse OMR project is actually trying to make forward motion on these fronts. So if you haven't heard of Eclipse OMR, it's an open source project that was created about a couple of years ago, 2016, beginning of 2016. It has a series of technology components for building language runtimes. So language agnostic components written in C and C++ for implementing threading libraries, platform porting libraries, garbage collectors, just-in-time compilers, and other things. It's available on GitHub. It's with the Eclipse Foundation, so it's governed by the Eclipse Foundation rules, and it's a very permissive license, and we love people to show up and pick stuff up. So if you're interested in that sort of technology, this is a great project to get involved in. So let's start talking about the things that we're doing to try to tackle some of the problems that I mentioned before. How can we make it easier for non-compiler developers to write code that generates native code? So the first question I'll ask is, so what's the interface to most compilers? Why is that hard? Basically, if you look at it, these are functions to build intermediate language of things like, you know, for example, LLVM is routines to build SSA. And you, sorry?
Well, you don't really need to know SSA to do LLVM. As in, you know, you do a locus for your local variables, and then, you know, after you run SROA, it will turn them, you know, into SSA form. Okay, all right. So, so maybe I'm wrong about this point. However, the interfaces that I've seen have tended to be still fairly low level and relatively close to what the intermediate language of LLVM is. I'm not trying to pick on LLVM here. It's just an observation that I've made in my looking around at this problem. All right. So anyway, my argument was here that you would have to understand SSA to really do a good job of generating intermediate language, just to tell the compiler what it is that you want to compile. In any case, that's why I created this JIT Builder library that I mentioned at the beginning of the talk here. So the goal here was to create a higher level API that could evolve independently of the compiler IL. So it provides a bridge between, or is intended to create a bridge between what software developers want to do and how the compiler translates those operations into lower level statements. So we want to make it easy to describe the structure of data. We want to make it easy to describe the structure of functions and expose no details of the compiler IL. It's still a relatively lower level API at the moment. It's basically targeting people who understand procedural languages, which, yes, that's a little bit dated these days with the languages that people are interested in. But it's an API that's still evolving up. And I just wanted to give a few examples to make this a little bit more concrete in people's heads. So this is our most simple example of a JIT Builder code. So in JIT Builder, you write a thing called a method builder. You extend a method builder. And in the constructor, you define how you're going to call this function that you're trying to generate dynamically at runtime. So you can give it a name. You can define parameters and say this is a 32-bit integer value that's going to be called value. It will have a return type that's a 32-bit integer. And so that defines kind of the ABI to this function that I'm going to generate dynamically. And then on the right side, you implement a callback called buildIL, which just takes a series of calls that you can load a value, you can define a 32-bit constant, 1, add them together, and then return it from the function. And this is basically how you specify the operations that the function that you're trying to generate is going to do. Now, this doesn't look very easy to write for a human, but the purpose of this is not to make it easy for humans to write. Its purpose is to make it easier for programs to write. Right? This is an API that's designed for programs to be able to generate code readily at runtime. So just a slightly more complicated example, the famous Fibonacci code with JIT Builder. So the function on the left is the thing that we're trying to generate. You start with a method builder, and then you do calls on the method builder. You can create an if-then-else structure very simply by passing in places to create new builder objects called then builder and else builder here. And then what if then else is going to do is it's going to insert all this code in here and create the control flow structure in the IL for you, so you don't have to worry about how to do that correctly. And then it places these kind of templates where you can put more stuff to describe what happens on the two branches of the if-then statement. In this particular case, I didn't have to create objects, I just passed them in, and if-then else would create them for me. If I had code already defined, I could pass those in and it would just connect them up into the control structure that I need. And then I can go from builder to builder and just inject operations, right? So on this path, I can load n and just return it. On the else path, I can do the more complicated stuff to calculate n-1 and pass that to fib, and n-2 and pass that to fib, add the results together. And I'm missing a return in this case. So that's not great. Should be a return on top of here, returning the result from the add on this path. So, you know, this is an if-then-else. There are services for creating for loops, for creating while loops, and do loops. And the basic idea is to just meet developers and with constructs that map what they're used to seeing when they write their code. So that if they're trying to generate a function, they can kind of model in their head what that function should look like because it's using constructs that they would be familiar with. So it has lots of lower level constructs, like I mentioned. You can do conditional structures, you can do looping, very familiar procedural concepts at this point. We're looking to actually improve that and keep pushing that API up. We have increased support because most of the people who are at the OMR project right now are JIT developers who are interested in building JITs for language runtimes. We have been pushing in the direction of trying to model virtual machine states, so that's one of the areas in which we've been pushing the API up to try to get to a point where you only have to describe what the virtual machine looks like, and then you can automatically build an interpreter and a JIT compiler from that virtual machine state. It's not quite there yet, but we are making great strides there. We have a thing that can model an operand stack, which is a very common thing that you see in bytecode-based virtual machines, which enables much better JIT optimization for manipulations of the operand stack. Basically, it eliminates the whole pushing and popping from memory operations completely from the method, and you can just use local variables, which then gets register allocated. However, this section, while very interesting to JIT developers working on languages, is probably not of interest to most software developers. So that's an interesting side note, but it's not the direction that I think we need to be pushing the API here. We're all the time adding new services, and we're always looking for more, just to, again, push that API up and meet developers where they are. So vector loop builder is an example of that. It's a way of specifying a vector loop to where you only have to write the code once. It will automatically generate both the vector loops and the scalar loop from the code that you write. Now you might be thinking, you know, one of the things I mentioned is the developers are using lots of different languages, and all the examples I showed are C++. So that's not great, right? So how can we enable developers to be able to access this API natively in their language of choice? There was a talk earlier today in the Turbo workshop, which if you didn't attend, I highly encourage, because there's some very interesting stuff being done in that workshop, and it continues on tomorrow as well. An interesting talk was this morning about how to take the JIT Builder API and move it from being a set of C++ classes that you interact with to actually creating a data representation of the API stored in a JSON file. And then we can write a generator that processes that JSON file and generates what we call a language binding for the API. And what we've done to date is create that file, create a schema so that we can validate it, and then we have a generator that goes back to C++. So we're back at square one, but it works. And what we're now working on is the C-based language binding for that. And once we have the C-based binding, then we should be able to expand out to a lot of different languages. And the idea here isn't to necessarily faithfully replicate exactly how the JIT Builder API works in C++, because that would be a sort of mismatch in terms of programming idiom with other languages. The idea is that having a generator per language will allow us to idiomize or make the API faithful to the idioms and the way people program in the different languages. So you might program JIT Builder slightly differently in Python than you would in Ruby than you would in Rust. But that's the basic plan. And we're trying to branch out to a lot of different places. The idea of using generators is a way to reduce cost for us to support n different languages without necessarily having to do work in n different places every time we expand our API. if we have a generator and an API that sort of operates consistently, we're hoping that most of the time we won't have to change the generator when we add new API. It will just be updating the data file and then regenerate the binding, and it will become accessible to all kinds of different languages. So it's cheaper for us to maintain and allows us to reach out to a lot more developers.
So I just wanted to show you one little example. You probably can't see in the back, sorry. But this is what the JSON file looks like for one particular service in the JIT Builder API. And so this example is a transaction API so that you can actually fire off a hardware transactional memory transaction. So you can inject operations into here that will operate under the transaction. If you have a transient failure, say you had two transactions that conflicted with one another, wrote and read to the same location, you would get a transient failure. So what do you do when that happens is in this builder, and then you can specify what happens if you have a persistent failure builder. Like, so if you happen to put an operation into the transaction that isn't supported by the hardware as a transactional memory operation, you would end up executing the code here. And that also provides us an easy way, if you don't have support for hardware transactional memory, you end up just running this code. And you can see that there's a line here for each one of the parameters in the service and descriptions of what those parameters are. So you can process the data and then generate the header files or whatever is appropriate in the language of your choice. And then once we've got generators for different languages, that means we can generate efficient native code natively from the different languages, which means we have an easy JIT Builder API that generates efficient native code and is available from a lot of different languages. But we're still left with the problem of how do we overcome the dynamic cost of being able of doing all of this at runtime, right? When you look at JIT compilers, they consume CPU cycles, sometimes lots of them. They consume memory dynamically, and sometimes a lot of it. And it takes time until the compiled code is ready. And you have to sort of measure that against the time that it's going to take to complete the task. An in-process JIT, which is kind of the traditional approach to this, is going to have a tough challenge in a lot of cases here, right? Because it has to do all that work and pay all the CPU cost and all the memory costs up front, and then hopefully it can get you code fast enough that you can actually accelerate the task that you're running. And that can probably work for very long-running or repetitive tasks, which is great. So that's why some people have been actually using this technique, because they're working in problem areas where it's actually good enough. But there's clearly a cost-benefit analysis here that's going to affect where you're going to be able to do this profitably. But what if you could move that JIT compilation effort somewhere else so that it didn't have to impact the runtime of a program? Maybe you could move it off onto some other cloud resource, or you could aggregate the JIT work from multiple clients, and you could look at what problems are a large number of clients trying to solve, so that you could use this separate resource to compile only the problems that are kind of commonly being solved across a cluster, say, and then be able to deliver code from earlier compilation requests if the same compile problem is actually being requested, and being able to classify compiles that are almost the same, so that you can maybe share more code, or you can provide more optimized code. You can have sort of control over that trade-off. And so if you could do some of these things, that would clearly allow you to really change the cost-benefit equation for when you might be able to do this dynamic compilation solution to this problem. And so we call this kind of an approach JIT as a service, and I have a couple of demos that I'm going to do now to try to show you how this can work. So we have a couple of prototypes. One of them is in the Eclipse OMR project. So it's in a much simpler project. And then I have a second example, which is in the Eclipse OpenJ9 project, and that one's a much more complicated one. So I'll start with a simple one. So the first demo was a project that was done by a set of Extreme Blue students. So IBM has this program called Extreme Blue, where we have top students come in, and we have a set of problems that we match students to. And so 4 students get to work on a problem they get about 6 weeks to work on a technical problem. They also have to do a bunch of business analysis to see whether the business it would be interested in solving this problem, if it's interesting enough to the business. And they have to go through a series of like Dragon's Den type production or proof of concept kind of conversations, which is kind
kind of fun for the students. I'm only going to tell you about the technical stuff that was done as part of this, but it's actually kind of a cool program. So the idea here is that we're going to take JIT Builder API calls and basically create a record, a log of what those calls are, and in such a way that we can take that log and transfer it to a different computer and replay the calls on a JIT server that could potentially be on a different machine. And so we record the calls, we send it to the server. If the server hasn't generated code for this particular input before, it replays it into the JIT server and compiles the code, and then can store it in a hash table. It can just remember, can cache the code that is generated using the record as a key. You can send the code back to the client installs the code into its code cache, and then it can be called just like it's a C function, as a function pointer. And so this project team created a JIT for an ultra simple but Turing complete language called BF, brainfuck. And it's quite the language if you've looked at it. So at this point I'm going to do a very low-tech switch to a second computer to show you the, actually I shouldn't do it that way. Just keep that there. It's going to look great on the video. Unfortunately, this is the technology we have available to us in 2018. Okay, so this window is actually remote served from this laptop over here, right? So by this network cable. And so we could start up the server very easily just by running Imperium is the name of the project, so we call it the Imperium server. And so it just starts up and now it's waiting for requests. So let's go and go to this one over here. And before I show you running, well, that didn't work. There. Is that more readable from the back? There, maybe? I wanted to show you what a VF program looks like. It's only got 8 bytecodes or 8 sort of statements that you can make, and they're all, it looks like gobbledygook when you read it. So this guy, Eric Bossman, all credit to him, he went and wrote one of these programs somehow that actually generates a text-based Mandelbrot output. And there's actually more to it. So that's quite an achievement in and of itself. I don't know how we did that. But we can send, so BF is the runtime that we've compiled. It has a lightweight JIT client in it that's going to connect to this server over here on my little network at this port, and it's going to run my Mandelbrot program. And the first time we do this, it's going to take a while. In part because that language is pretty awful to compile, and in part because, well, that didn't turn out very well, sorry. I'm going to have to make this smaller. There you can see. That's the Mandelbrot, right? Everybody recognizes that famous picture. And you won't be able to read it, so I'll read it for you. It's basically 7.5 seconds that it took before it got a response from the server. And that's because it's actually, part of this is not the fault of the server or the client, it's the way that the students had to accomplish this in 6 weeks. So point in time that it's going to take that long. But anyway, but if we do this again, you'll see we get it almost immediately. And that's because the server is actually able to respond very quickly the second time. Let's see if I get back to the server window here. So you can see the first request, 7.3 of those seconds was compiling, and the second time, 64 microseconds. So very, very quick. It was able to just pull it out of the cache and send it back right away, because you're compiling it exactly the same thing. And 64 is actually a big number, so I'm going to try that one more time and see if I can get, okay, down to 25. 12 is the number that I've been getting every other time that I ran this, so. I'm a little surprised that it's that big, but still, the point is very good. Like, it's not taking 7.5 seconds anymore, it's only taking 12 microseconds. And so, in a scenario where some other service has asked for something to be compiled, then the next guy along doesn't actually have to pay a very high cost in terms of memory or CPU or even time to get the code back. Okay, so that's my first demo. Now I have to do the low-text switch again.
So,
If I can do that faster.
so what's the granularity of the request, right? Is it per method?
Yes.
Things are getting defined?
Yes. Yes, in that particular case, it's per method. Well, in fact, in both of these prototypes, it's a method-based granularity. But that's just a kind of where we are with it. Okay, so that looks neat, but it's a text-based Mandelbrot thing written in some crazy. Okay, I shouldn't insult BF. It's an interesting language, but I doubt anyone has ever really used BF to do anything serious in it, right? But would this really work for real? So we've also done a prototype for JIT as a service in our JVM project, our open source JVM project called Eclipse J9, which, quick plug, this is the IBM J9 Java virtual machine, which has been used it's been under development for 20 years. It runs all of IBM's software stack, and it's used by all our customers. So, just as a proof point, if you've done any online banking transactions in the last little while, probably at least part of that ran on this guy. So it's real. It's a very real sense, because I like getting my paycheck, and I like getting all my other things that I do with my bank. So it's very good. And we've been doing releases. We're basically tracking OpenJDK. We use OpenJDK for class libraries, and this is a JVM project. So we continue to pump new investment in the technology areas to make the JVM run Java programs better without changing the API that the Java programs have. All right, enough plugging OpenJ9. So we've also done a project in OpenJ9 to explore this JIT as a service architecture to see how well it can work there. So basic idea, it's the same thing that I showed you before. It's a client-server model with bidirectional communication in this case. The client is actually watching the application still, counting method invocations and sampling to find out which methods are taking time and identifying the ones that need to be compiled. And then when the client finds a method that needs to be compiled, it sends a request across to the server. The server, through the course of compiling that code, will have to ask questions, and the client will have to answer questions about the state of the current VM. And it'll ask about other classes, about other methods. Once it's finished, it will send the resulting code back across to the client. The client will install the code in its code cache, and you're off to the races. And we will now move to the second demo with our ultra high-tech switching fabric. Let's go to a different window, which is over here. All right, so let me just start servers. Okay. Yeah. Okay. So this demo, I'm just getting the servers up and running. So while that happens, I'm going to tell you about the demo and what it's going to show you. So in this particular demo, I'm going to be showing 3 different configurations of OpenLiberty, which is an application server, running a benchmark called Acme Air, which is a Java EE7 benchmark. It's a fairly significant benchmark. It's modeling a flight reservation system for an airline. So people, it's a nice little demo. And these 3 configurations, I'm going to make the JVMs run, the servers run in a fairly constrained environment for Java. I'm only going to give them half a core of CPU and 256 megabytes of memory. And so I'm going to run one configuration with hotspot, that's going to be the orange data. I'm going to run one with OpenJ9, that's the blue data. So that's 1 server each. And so those servers are going to operate in the constraints that I showed before, that I talked about before. And they're all both going to have a JIT inside in their own process. And then the third configuration is this green one, which is going to run OpenJ9 with no local JIT. So all the JIT compilations that it does are going to go across the wire and be compiled by, well, actually the servers are running on this laptop, and then the compiles are happening over the network cable and coming to this laptop, which is running the JIT server. And you can see these servers just started up, and you can see there was a spike in compilation activity that was required by those 2 servers to run here. And I'm running 2 servers just to show that I can connect 2 JVMs to the same JIT compile service, and it stands up and still works. So these are not drop-in replacement configurations. I'm not trying to tell you that you can take 2 J9s and run them in the same space that you can run a hotspot. But
You can see, for example, from this graph that Hotspot is very happy to use almost as much memory as you tell it has access to. OpenJ9 with the JIT is running with, this is just one server, so it's running in a very frugal amount of memory. It's not trying to push things too hard. And the two OpenJ9 servers are using roughly twice the memory of one server, and still less than what Hotspot's using. All right, so this graph is showing memory, resident set size. This is showing CPU on the servers. This graph is going to show the reported throughput once I start applying load, which I haven't done yet, so maybe I should do that. After typing my password, there it goes. And so in a few seconds, because there's a time lag for the monitoring software, incidentally I'm using Telegraph, Influx, and Grafana to do this monitoring thing. So the software is pretty cool. It took a while to set up, but once I got it set up, it's very nice. Working very well. Okay, so we're starting to see throughput now. So the OpenJ9 server starts off very, very quickly. And that's because I've used an option called -xtune virtualize, which basically tries to take advantage of as much cached JIT code as it can. OpenJ9 has a class sharing, a shared classes cache, in which it can store JIT compiled code from previous runs. So I've done a previous run, I've populated a cache with a bunch of AOT code, or JIT, cached JIT code. We call it dynamic AOT, so that's why I call it AOT. And so it can start up very quickly because it's just loading code out of that cache. However, it is still going to have some memory spikes. You'll see a little bit of memory spikes here from JIT compilation activity that's still happening because that dynamic, that cached JIT code is not quite as fast as JITted code can be. And so it's going to still have to do recompilations in order to get its performance to its peak level. You can see that our servers that have no JIT inside them took a while to kind of reach the same level. And remember, this is 2 servers compared to 1 server, so it's not really in a state where it's really taken over the world yet, but it has already surpassed at least where OpenJ9 and Hotspot are doing. Hotspot's struggling to get enough compilations done in that half core of CPU, as well as handle all the transactions that are being pushed into the server by the load driver. And so now you can see that this guy's really taking over because of all the compilation activity. Here's finally paying off. And the no-JIT servers are together now providing a lot more than twice the throughput. So I'm probably not going to be able to spend, and you don't want to sit here and wait for 20 minutes to see the end game of this. So I'm going to again switch back to the main presentation just so that I can show you green screen. All right, so that I can show you. So this is the final run data that I showed at the Oracle Code 1 keynote a couple of weeks back. So after 20 minutes, you can see that Hotspot is eventually catching up. This -xtune virtualized option that I mentioned comes with a slight bit of a throughput problem because it's trying to inhibit recompilations in order to make sure it can get the ramp up very quick. So it ramps up very quickly, but then Hotspot eventually does catch up and surpass it by a little bit. But in general, the ramp up that it gets is more than pays off for this long-term throughput, especially if your JVM is short running. Remember, this is 20 minutes. That's way longer than most people will run a benchmark. And on top of that, the OpenJ9 servers that are running with this remote JIT, because I've managed to move all this work over here, it can ramp up much higher. And in fact, it even gets to more than twice the throughput, even after 20 minutes of the other 2 servers. And I don't really have a solid explanation for that, other than a theory that because we're having to do so much stuff in such a drawn-out period of time, the profile data that's used for a lot of the compiles isn't high caliber. And so we're not really doing the compiles that we really want to do. In either Hotspot, OpenJ9 is doing the compiles that it wants. I'm not sure exactly what Hotspot's doing there. Okay, so I think I've talked about how we can make it easier for people to generate native code directly from their language of choice. And now I think with this JIT as a service model where we've managed to change the cost-benefit equation, or at least we have the potential to change the cost-benefit equation for how we deliver compiled code to a running application, particularly in the cloud, but really across any cluster of machines where you can afford to deploy a JIT service. So where can we go with all of this? So current state right now, before I go to where we can go, is, so we've got lots of plumbing completed. So these prototypes that we've got are basically demonstrating that it's possible to do all these things. And the IBM production team, which is working at the OMAR and OpenJ9 projects, is now actively pushing forward in both of these projects and trying to make these things more real, trying to get things merged into the master branch and finalized. There's lots of projects here, so I know I've focused here on Eclipse, OpenJ9, and OMR, so it sounds like I'm really plugging those projects, and I am. But, but there are pieces of this at other projects, and so I don't want to necessarily portray this as we're the only ones who know what we're doing here. There are lots of other projects that are doing work here that's relevant and that would be very able to feature this as well. So LLVM obviously has had for quite a while now, they've had a remote JIT compilation service code. I'm not aware of anything actually using it in any sort of production sense, but I could be wrong about that. I'm not a close LLVM watcher. Maybe you know.
I don't think so.
So it's still a very interesting facility that's there.
And I think the biggest issue is that LLVM, was designed for a static compilation, which means, when you're JITting with LLVM, it takes quite a long time.
Right, right. So there is that service is there, and LLVM is available, and obviously lots of people are familiar with LLVM. If you're a Java developer, there's obviously the Truffle project in the Java ecosystem, which is another way of approaching the problem, making it easier for people to generate native code directly from their applications using ASTs, and it has a very direct hookup with the Graal compiler, which is a very good project in the Java ecosystem. GCC has a libjit project, which I'm not aware that there are people using this. I think the Ruby community might be using libjit at this point, or moving towards using it. But I don't know very much about it. So if you want to look into that one, if that's attractive to you, that's someplace you can go look. And I'm sure there are others. I'm not claiming that this is a comprehensive list. But going forward, what we're doing is, so we're continuing to expand out the number of languages that you can access JIT Builder from. So right now, I know we're only at C++, but we're trying to grow that out so that we can reach developers in all kinds of different language communities. We are working to expand the API to try to push further upwards so that we can meet developers at a level that they're comfortable working at the level that they're working at in their current programs. It would be very interesting, I think, to start looking at generating dynamic, specialized data structures for specific arrangements of data, right? Like if you need a hash map that goes into double in a language where you just talk about objects, you can generate much more efficient code if you know exactly the types that you're working with. And so JIT Builder is an excellent way that you can actually create this kind of thing. So it could be int to double, but it could also be like arbitrary structs of things that you could be mapping as keys and values, and executing very efficient native code to access those data structures directly at runtime for the problem that you're solving, right? We're trying to improve our support for vectorization and for parallel support. So OpenJ9 has auto-parallelization and auto-synthesization inside it. We haven't yet sunk that into OMAR or to access it from JIT Builder, but we're trying to do that. We're trying to build new APIs for allowing people to specify that they have a vector workload so that it doesn't, you don't necessarily rely on the compiler to prove it. You can just, I know this is a parallel operation, just do it in parallel. And obviously we would love to be able to target developers who are using different paradigms than just the simple procedural stuff that we have so far. We really want to push forward on this accelerating tasks, not just writing JITs for languages. I listed a few examples of a few projects here where I think we could provide some acceleration, and having a JIT service that could look across a cluster of use cases and pick and choose the right ones to be compiling so that you can accelerate the use of these types of projects across that cluster, across the cloud, is a very interesting area to expand into here. And I have some ideas, but really I'd love to hear what other people think about areas that we could expand into here. And very interested in working with people to do that. that. Finally, this JIT as a service opens up a whole host of opportunities to increase the optimization and to use machine learning to try and classify what things are happening in the runtime spread across a large set of systems, right? With the move to cloud and the move to microservice architectures where you don't have a single monolithic application, you have tens or even hundreds of microservices all running in different runtimes, all potentially running some code that's the same and some code that's different. Trying to figure out how we can optimize better across that network of applications and runtimes is, I think, a very interesting area to work on here. And the fact that we have multiple runtimes means we also have an opportunity to start spreading out some of the overheads that we would normally have to pay in a single runtime. We might be able to collect more rich profile data by collecting bits and pieces from the parts of the runtimes in a cluster that are doing similar things. If you want to learn more, there's lots of stuff out there in the open. OMR project website, GitHub repo, and Slack channel, where most of the team is listening on the Slack channel. There's the Turbo workshop today that's been in the Stewart room. It's almost over today, but there's another session tomorrow, which is looking at how to incorporate some of the GC technology that's in OMR to be able to leverage it to manage your own memory in a very simple way using our object model support. And Eclipse OpenJ9 also has a website, repo, and a corresponding Slack channel where you can reach out and talk to us about the JIT as a service demo that we've got, or about the JVM in general if you're interested. And if you want to learn more about JIT Builder, you can just Google it, because most of the top good pages tend to come up on the Google search page. And I'll stop here. Thank you.
Right, so we've got, I think, yeah, so we've got 8 minutes left. Right. Here you go.
Hi, thanks, very interesting talk. My name's Ayan, I work on the JIT for MATLAB.
Oh, yeah.
So one of the things I noticed is in your examples, I don't know if it's by design, you talked about JITs for statically compiled, or statically typed languages, sorry, not statically compiled. So one of the big technological blocks in out-of-process JIT for a dynamically typed language is that there's so much of process-specific information related to the types and such and things that pretty much by trying to, so you have two options. Either you marshal in and marshal out all of that, or you have the offline JIT create something that's process agnostic and then patch it up. Both of these are, we found prohibitive in practice. Have you had any experiences around that?
So not so well. Okay, so in the OpenJ9 Java virtual machine, there are actually two types of copious data that we're collecting while the program is running, usually in process, right? So we're collecting lots of profile data about the types that are being sent in as arguments to function calls, what types are being used to do check casts and instance ofs, what type of which basic blocks are executing in methods, right? So relatively rich, but it generates megabytes worth of data. And so in the JIT as a service demo that I showed you there, the prototype, what we're actually passing that information across to the JIT service for it to maintain. So for every client that connects to the server, it creates a set of session data. And one of the aspects of that session data is the profile data that's being put there. And the way that we manage that is by only sending basically the updates to the profile data since the last time that we talked to the server. So the client is kind of caching data as it goes, and the more code you compile, the less you're profiling, so it kind of works out. We also have part of our profiling framework that we're using going forward is actually using JIT code to compile profile data, but do it in a very smart way, so that if the code is running the way that we expected when we compiled it, you don't generate very much profile data. But when you go off the beaten track, then you start collecting data, and then when you collect it,
regularly by the production code.
Yeah.
So there's that, and then there's a second piece of data, which is actually the class hierarchy data, which is also megabytes and megabytes worth of data, right? Especially in a Java EE program. So one of the things I forgot to mention during the demo, which I'll take this opportunity to say, is each of the Open Liberty servers that's running in the remote JIT, using with the remote JIT service, it's compiling roughly 8,000 to 9,000 methods, each one of those JVM servers at the JIT server. And it's compiling it with fairly aggressive optimizations using our warm optimization level, which is basically the optimization level that's the most effective in application servers. So it's doing a lot of very aggressive optimizations, and it's inlining anywhere from 0 to 100 methods into the method that's actually being compiled. So there's quite a lot of complexity in this prototype that's enabling it to reach the same level of performance that you would get from an in-process JIT. And the class hierarchy table is a big feature that enables that to do it, right? Because in-process JITs, especially in the Java ecosystem, rely on speculative execution. They need to know what the state of the class hierarchy is now so that they can make the right decisions about what things to inline and what things not to inline. And so we need the class hierarchy table in order to reach that same level of performance. And so we do the same thing with it. It's the updates that have happened since the last compile request has happened are transferred across. And so if you don't need to do any compilations, you don't need to send anything across, even if you've collected lots of it, well, you might get toasted the first. If you compile a method late, you might end up sending quite a lot of data. These are parts of the prototype that we just have to, those are rough corners, we need to shave them off. But, yeah.
Right, so any other questions, folks? No?
Right then, so
Thank you.
thank you.
Thanks very much.